Good day everyone. Today we are going to start chapter 2, that is Electrochemistry of class 12. We are going to complete this chapter with a detailed explanation and NCERT reading and going to solve few questions. So first, let us try to understand what is electrochemistry. So basically, it is a branch that deals with the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to carry out the non-spontaneous transformations. So a large number of systems such as energy converter and storage, fuel cells, battery systems, industrial synthesis and production of various chemicals involves these electrochemical methods. So electrochemistry brings advancement by making reactions energy efficient as well as eco-friendly. Therefore, it is very important to study about electrochemistry. So first, let us try to understand what are redox reactions. So redox reactions are those reactions where we see both the loss of electrons and the gain of electrons. Losing of electrons is called oxidation, gain of electrons is called reduction. So redox reactions will involve both oxidation and reduction. And these both reactions are complementary and occur side by side. Let's take an example. So here we have H2S plus Cl2 will give rise to S plus 2HCl. So here this is going to lose its electrons, means oxidation will happen, while the Cl2 will gain electrons, that means reduction is happening. So here both oxidation and reduction are happening, so it is a redox reaction. So here in these reactions we can observe the transfer of electrons, and therefore it will be a cause to generate electricity. Therefore, redox reactions will set up the basis for electrochemical cells. So now let us understand what is an electrochemical cell. So it is a device in which the chemical energy of the redox reactions is converted into electrical energy, and in the electrolytic cell is a device in which the electrical energy is converted into chemical energy. So they function vice versa, and this is the reaction. And the most common electrochemical cell is the galvanic cell or the voltaic cell, and a galvanic cell is the modified form of Daniell cell. So this is the following reaction for a Daniell cell with an electric potential of 1.1 volt, and this is the concentration of the used ions. So we know that galvanic cell are the electrochemical cells which convert the chemical energy of a spontaneous redox reaction into electrical energy. So in these cells we basically will place an electrode in a solution of its own salt. So suppose if we place Zn electrode, then this salt will also be belonging to zinc, such as zinc sulfate or anything like that. And this combination is called a half cell. Or a redox couple. So in a half cell, either reduction can happen or oxidation can happen. So oxidation will occur at anode, that is, it is the source of negative electrons, while reduction occurs at the cathode and it is the receiver and it will become positive. So you have to always remember, oxidation will occur at anode and reduction will occur at cathode. And these processes of oxidation and reduction result in the formation of potential difference between the two half cells and hence generate electricity. So now we'll study about Daniell cell. So this cell consists of two metals or electrodes, that is zinc and copper, and the zinc rod will be mixed or placed in the zinc sulfate solution and the copper rod will be placed in the copper sulfate. So these both make up an half cell and this will make up another half cell, and these two solutions are connected by electric current and a salt bridge is placed. So here we have the zinc electrode and this is the solution of salt of zinc. Same here, the copper and the salt of copper, and electricity is connected and we have a voltmeter, and the two half cells are connected by a voltmeter and a switch externally, and the electrolytes are connected internally with a salt bridge, and both the electrodes will be dipped in some same electrolytic situation. In such case, salt bridge is not required. So if we place both the rods in the same solution, then salt bridge is not required. Now we will see the half cell reactions. So here basically we can understand that this is negative and this is positive. That means this functions as a oxidation half cell while this functions as a reduction half cell. This is anode and this is cathode, and therefore electrons will flow from here, that is it will release the electrons while this will receive the electrons. So zinc is on the oxidation side, it means it will lose the electrons, so oxidation is taking place, so this will be the reaction, that is it is losing 2 electrons, while copper will receive these 2 electrons and it will undergo reduction. So when we combine both these reactions, we can get this reaction by cancelling both the electrons. Now we will study what will happen if we apply an external voltage to this cell. So in case 1, that is when the electric potential is lower than 1.1 volt. So we know that this Daniell cell will produce a electric potential of 1.1 volt. So if we apply an external voltage which is lower than 1.1 volt, then the electrons will as usual flow from the zinc rod to the copper rod, and hence the current will flow from copper to zinc in the opposite way of the electrons, and hence there will be no change because in the same way here the copper will get deposited. And then in the case 2, when the external voltage is applied equal to 1.1 volt, then the cell reaction will stop and there is no flow of electrons and therefore no flow of electricity. In the case 3, when the external potential is more than 1.1 volt, then the reactions will get reversed, which also reverses the polarity of the electrodes. So in that case it will become an electrolytic cell. So electrochemical cell will become electrolytic cell, and now the flow of electrons will be from copper to zinc, and therefore zinc will get deposited while copper will be depleted. It works quite opposite to the electrochemical cell. So now we will understand what is a salt bridge. So it is basically a U-shaped glass tube containing electrolytes such as KCl, KNO, NH4Cl mixed in some kind of gel like gelatin or agar-agar. It plays a very important role in working of an electrochemical cell and it completes the circuit and maintains the electrical neutrality of the solutions in each of the respective half cells. So meter bridge will be the connection between the two half cells and will maintain the neutrality in between. So basically, the salt bridge is added in this Daniell cell was a modified form of the original galvanic cell, because the electricity flow stops after some time as the positive charge accumulates at the oxidation half cell and the reduction negative at the reduction half cell, and which balance the redox free energy and hence stops the redox reactions in our original galvanic cell. But in the modified galvanic cell, we can find that the salt bridge is present and it provides the anions and cations to the respective half cells and thus maintain the neutrality of the half cells. So salt bridge is very important in this whole functioning of electrochemical cell, so that it will not stop and continue to happen. Now let us study some important terms related to a cell. So first we'll study about electrode potential. So what is electrode potential? It is the potential difference which is developed between electrode and electrolyte. That means when we dip an electrode in electrolyte, then there will be some potential difference which will be generated, which is known as electrode potential. So electrode potential can be of two, that is oxidation potential and reduction potential. So we have both the cells, that is oxidation half cell and reduction half cell. So here in the oxidation half cell we have oxidation potential, and the reduction half cell we have reduction potential. Moving to the next one, that is cell potential. So the cell potential is the potential difference between two electrodes, that is the two half cells, and the formula is E naught of cell is equal to E naught of cathode minus E naught of anode. Here we can understand that cathode reduction will occur, anode oxidation will occur. So it is the difference between the standard reduction potential and the standard oxidation potential. That means we have the difference between the standard reduction potential of cathode and the standard reduction potential of anode, and it depends on the following factors, that is nature of the metal and its ions, concentration of electrolytes used, and the heat which is provided. Now cell potential is the same as electromotive force, that is EMF, when no current will flow through it. This is a very important point to note. Now we'll study how we'll represent what is a cell representation. So it has basically three steps. First, we will write down the reaction which is happening, and then we'll write down the half cell reaction. So we'll break down this reaction into two reactions, oxidation reaction and reduction reaction, and then we will write the cell representation. So for this, how we will start? So remember the word lone. Here in the left we have oxidation in the anode side and it is negative. Remember these, in the left we have oxidation which is anode and it is negative. I'll explain the cell representation with this example in a while. First we'll complete what is the standard electrode potential. So under certain conditions, the electrode potential under certain conditions, that is these are the conditions. That means the concentration of the species should be this much and the pressure should be this much, and it should be under 25 degrees Celsius. And according to IUPAC, the standard reduction potential is only considered as the standard electrode potential. So here the standard reduction potential is also equal to standard oxidation potential, but the signs will be reversed. Now we will understand what is the measurement of electrode potential. So how do we actually calculate what is the standard reduction potential of any metal? So it will be done with the help of standard hydrogen electrode. It is represented in this way. and the reaction will occur like this. So here we can observe that this basically consists of a platinum electrode which is placed or coated with platinum black and dipped in a solution of H plus ions, and pure H2 gas is sent with high pressure. So here the electrode has zero potential at all the temperatures. So this will have zero potential at all the temperatures. So you can easily find out the potential of the other cells which we are placing in connection with this half cell. So we can measure the EMF by combining this standard hydrogen electrode of the anode with an other half cell of cathode, resulting in the standard reduction potential of the other half cell, that is the cathode. So in this manner we can study the half cells which can be measured easily. So here this is the reaction in which we already know that the She electrode potential is 0, so we can easily find out the standard reduction potential of our required half cell. So here this is a cell in which we know that this will be 0, so you can easily find out, and we found out that 0.34 volt will be the EMF of this half cell. In the same way, for zinc we have found it to be minus 0.76. So here we can simply understand that the positive value of the electrode half cell in the first case indicates that Cu2 plus ions get reduced more easily than H plus ions. So hydrogen gas can reduce copper under certain conditions, and thus copper will not mix up in HCl. So this will be taken in the oxidation half cell, and this will be taken in the reduction half cell, and the overall reaction will be like this. And we can calculate the EMF, that is what is taken in the right side minus of what is taken in the left side. So we can get the electrode potential to be 1.10 volt. So we have some inert electrodes. Those are some metals like platinum or gold are used as inert electrodes. They do not actually participate in the reaction but provide their surface for oxidation or reduction reactions and for the conduction of electrons. So here also the platinum is actually inert electrode. So it will not actually perform the reaction but help us to actually find out the reduction potentials of other half cells. Now we'll see how actually we will write the cell reaction. So here we can observe that there is a loss of electrons. So this will undergo oxidation, and here there is a gain of electrons, that means Fe will undergo reduction. So oxidation will be written in the left side and reduction will be written in the right side, and these both will be separated with a double line, that means it is a salt bridge. So here Cr and Cr3 plus, so we'll write down like this, and Fe2 plus becomes Fe. So this will become the whole cell representation. Now we will do a quick reading to the NCERT. So here the chapter will start with the introduction of electrochemistry. It is the study of production of electricity from energy released during spontaneous reactions and the use of electrochemistry to bring out the non-spontaneous chemical transformations. And these are the importance of electrochemistry in this whole paragraph. And then they have told us what is a galvanic cell, voltaic cell, electrolytic cell, and the working of the electrochemical cells, and what will happen if we provide an external voltage. So here if the voltage is equal to the internal voltage, then the reaction will happen the same. It will stop, and if it is less, then the reaction will happen the same, but if it's more, then it will become an electrolytic cell. And then they've told us the working of the galvanic cell and the half cells or redox couples, reduction potential, electrode potential, and how do we measure electrode potential, that is using the standard hydrogen electrode. And these all are done, and this is completely done, and there are some in-text questions provided for you. So tomorrow we'll start with the calculation from the Nernst equation. Thank you so much for watching. Stay tuned for the next parts of this chapter. Thank you. Good day everyone. Today we are going to start part 2 of electrochemistry, and in this video we are going to complete electrochemical series and Nernst equation. First let's start with electrochemical series. So electrochemical series is the arrangement of various standard half cells in order of their decreasing values of standard reduction potentials. So it is arrangement of the standard reduction potentials of various half cells. It can be negative or positive. Negative E0 means that the redox couple is stronger reducing agent, while positive E0 means that the redox couple is a weaker reducing agent. So let us discuss the applications. First is the stability of the reduced form. So if the standard electrode potential of an electrode is greater than 0, then its reduced form is more stable as compared to hydrogen. Similarly, if the standard electrode potential is less than 0, that is negative value, the hydrogen gas is more stable than the reduced form of the species. Next is the nature of electrode. The electrode with higher electrode potential acts as a cathode, whereas electrode with lower electrode potential will act as anode. Reducing power of species, that is, standard reduction potential of the half cells are arranged from positive to negative. So more negative the EMF value, stronger is the reducing agent. More positive is the EMF value, the weaker is the reducing agent in comparison to hydrogen gas. So in our electrochemical series, Fe will be at the top and lithium plus will be at the bottom. And it also helps in predicting the redox reactions. So electrochemical series also helps to predict the feasibility of redox reaction, thermal stability of metal oxides, and spontaneity of an electrochemical cell by choosing the half cells with appropriate E0 values. So any cell reaction with negative calculated value of EMF will not proceed. Next, we'll study about the uses of electrochemical cells. So they are used for determining the pH of solutions, solubility product and equilibrium constant and other thermodynamic properties, and for potentiometric values. Now we'll study what is Nernst equation. So this is the equation which gives the relation between electrode potential, heat supplied and concentration of metal ions. So it is an equation which gives the relation between all the three factors. So first we will study about the Nernst equation for an electrode potential. So the standard potentials are always measured under standard conditions, that is 1 atm of pressure, 1 molar of concentration and 298 Kelvin. So let us first take this reaction, that is Mn plus n electrons will give rise to M, some metal. So the electrode potential measured against this can be written as this. So this is very important to remember that this is the equation called the Nernst equation. And for pure solids, this M is equal to 1. So the equation will become like this, that is E0 minus RT by NF ln 1 minus n plus 1. Here R is the universal gas constant, which is 8.314 joule kilo per kilomole, and F is the Faraday constant, whose approximate value is 96,500. So here next, the ln using logarithms will be converted into log, that is 2.303 will be multiplied. So the reaction will become as follows. And if we take 298 Kelvin and place the values of R and F, we'll get the reaction to be as follows, which is E0 minus 0.059 by N log 1 by M to the power N plus 1. Next we'll study the Nernst equation for EMF of a cell. We have completed the electrode potential for Nernst equation. Now Nernst equation for EMF of the cell. Let us take the Daniell cell. We know Daniell cell will have copper and zinc. These are the two respective equations, and 2 electrons are involved, and therefore in the place of N we take 2. For finding the cell potential, we'll subtract the anode from cathode. So we'll write the equations and take the ones which are common, and finally we'll get the equation to be E0 minus RT by 2F ln Zn2 plus by Cu2 plus. These are the concentrations of the ions. Now taking 298 Kelvin and R and F values, we get the final equation to be E0 cell minus 0.059 by 2 log Zn2 plus by Cu2 plus. Here we can understand that E cell is directly dependent upon the concentration of Cu2 plus and inversely dependent upon the concentration of Zn2 plus, and E cell decreases as the temperature decreases and the number of electrons involved in the reaction will increase. So let us take the general electrochemical reaction of this type, and the small letters are actually the stoichiometric coefficients. Then here we can write ln Q, and this can be later written in this form, where on top we'll write the products and down we'll write the reactants, and they are raised to the stoichiometric coefficients. So if we take 298 Kelvin and we substitute the R and F values, we get the reaction to be as follows. Now let us solve the question. So we are asked to calculate the EMF of the following cell at 25 degrees Celsius, and this is the cell representation, where E0 of Fe is given and E0 of H2 is also given. So from this representation we can understand the reaction to be Fe plus 2H plus will get raised to Fe2 plus plus H2. So here we will subtract the anode from cathode, and we get the E0 cell to be 0.44 volt. And the E cell can be calculated using the Nernst equation, and we are already given with these concentrations in the cell representation. So finally we get the answer to be 0.41 volt. Now let us study the equilibrium constant from a Nernst equation. How do we actually get the equilibrium constant from a Nernst equation? So let us take the Daniell cell, and this is the equation which we know. Zn plus Cu2 plus will give rise to Zn2 plus Cu, and the concentration of Zn2 plus keeps on increasing and the concentration of Cu2 plus keeps on decreasing with time. At the same time, the voltage of the cell on the voltmeter keeps on reducing. So after some time, there will be no change in the concentration of Zn2 plus and Cu2 plus ions, and at the same time the voltmeter will give 0 reading. So you can understand that at equilibrium the E0 cell is equal to 0, and so our Nernst equation can be equated to this, and when we bring the E0 cell this side, we get the equation to be as follows. That is, E0 cell is equal to 2.303 RT by 2F log Zn2 plus by Cu2 plus. So at equilibrium we can say that Zn2 plus by Cu2 plus is equal to constant, which is Kc. And at 298 Kelvin we can actually write the equation to be E0 cell is equal to 0.059 by 2 log Kc, which can be equated to 1.1 volt, which we know is the EMF for a Daniell cell. So keeping this value this side and substituting all the other values, we get the answer of Kc to be 2 into 10 to the power 37. And since such a high value of Kc is obtained, It shows that the reaction has proceeded almost to the completion before attainment of the equilibrium condition. And hence, the value of Kc will help us identify the extent of cell reaction. Let us solve a question. Here we are asked to calculate the equilibrium constant for the reaction. Fe plus Cd2 plus will give rise to Fe2 plus Cd. So here E0 value is given for Cd2 plus and for Fe2 plus. So we know that E0 of cathode minus E0 of anode. So we'll substitute these values and we'll get the E0 of cell to be 0.04 volt. And then we'll place this in the Nernst equation and get the final value of Kc to be 22.70. Now we'll study what is the concentration cells. So two electrodes of the same metal are placed separately in two solutions with same electrolyte having different concentrations, and these two are connected with a salt bridge. So this is called the concentration cells. Example is copper ion concentration cell. So the equation can be written, cell representation can be in this form, and this is the salt bridge and Cu2 plus slash Cu. Here it is Cu slash Cu2 plus salt bridge Cu2 plus slash Cu. So here the electrode placed in high concentration acts as a cathode and placed in low concentration will act as anode. So this is the whole construction of concentration cells. Now we'll study about the electrochemical cells and Gibbs energy of the reaction. So when a cell reaction will take place, the electrical energy is produced which can quantitatively be converted into work. So the electric work done by the cell results in corresponding decrease in the free energy of the cell. So the electric work which is done in 1 second is the product of EMF into the charge which is passed. So to obtain the maximum work from the galvanic cell, the charge has to be passed reversibly. So the reversible work done by the galvanic cell is equal to the decrease in the Gibbs energy. So we can write this equation by the statement. That is, work done is equal to negative of delta G. We know the delta G formula to be minus NFE cell. For standard conditions, we can write E0 cell. So then, by placing the value of E0, we can get the delta G0 is equal to minus 2.303 RT log Kc. Here E cell is an intrinsic property while delta G is an extensive property because it depends on the value of N. So now, at the stage of chemical equilibrium of a cell, the E cell is equal to 0. Subsequently, the delta G will also be equal because the formula is like this. So if the E cell is 0, then delta G will also be 0. So this reaction is only possible if E cell is positive and delta G is negative. So this is the chemical equilibrium. Now let us solve a question. The standard electrode potential for Daniell cell is given. So you have to calculate the delta G for this reaction, and the reaction is given. So simply by placing these values, we can get the answer to be delta G0 is equal to minus 2.12300 joule per mole. So we have completed the detailed explanation of electrochemical series and also the Nernst equation. So in the next video, we will be completing the conductivity of electrolytic solutions and its measurements, and we'll study the NCERT for both the parts at the same time. Thank you so much for watching. Stay tuned for more parts. Good day everyone. Today we are going to start with the part 3 of electrochemistry. We've already completed until the Nernst equation, and today we will be starting with the conductivity of electrolytic solutions and its measurements. So first, let us study some important terms related to conductance of electricity. So first we'll be studying about resistance. So resistance is defined as the hindrance provided by a conductor to the passage of electricity. So every substance offers resistance to the flow of electricity. It may be large or small in extent. So the electrical resistance R of any object is directly proportional to its length and is inversely proportional to the area of cross section. So, when we remove the proportionality sign, we get a constant which is called resistivity or specific resistance of the object. So now we'll study what is resistivity. So resistivity is defined as the resistance offered by a substance of 1 meter length with area of cross section equal to 1 meter square. So if we take the length to be 1 meter and area to be 1 meter square, then we'll get the resistivity of a substance. So the units are ohm, centimeter square by centimeter. So further we can write it to be ohm meter or ohm centimeter. Now we'll study what is the conductance. But the IUPAC will recommend the RAM as resistivity over specific resistance. Now conductance. So conductance is the ease with which current flows through a conductor. So it can be taken as inverse of resistance. So your G is equal to 1 by R, which is inverse of resistance. So we'll write the resistance formula and reverse it to get the final formula of conductance, that is Ka by L. So its SI unit is Siemens, which is ohm inverse. Now we study about conductivity. So the conductivity is the inverse of resistivity. So the conductance is inverse of resistance and the conductivity is inverse of resistivity. So conductivity is called specific conductance. It can be written as inverse of resistivity. So we'll get it to be like GL by A. So L by A is a cell constant. So we can define L by A as a cell constant. So we get the final value of conductivity to be G, that is conductance, into cell constant. So the unit will be 1 by ohm centimeter. And the factors which affect the conductivity are the temperature, nature of material, and the pressure. Now we'll be studying the different types of materials. So the first category of materials is the conductors. So these are the substances which have very large conductivity. For example, metals and their alloys, certain non-metals like carbon black, graphite, and some organic polymers are electronically conducting. Next, insulators. So these are the substances which have very low conductivity. Some of the examples are like glass, ceramics, etc. Next is the metallic conductors. So metallic conductors are those where the flow of electricity takes place due to the flow of electrons. That is, no flow of matter. So thus, the matter will not decompose. Due to the vibration of the kernels, the electrical conduction decreases with decrease in the temperature. Next is the electrolytic conductors. So here the flow of electricity takes place due to the flow of charge. That is, the matter will decompose into ions. So the electrical conductivity will increase. That is, the electrolytic conductivity will increase with the increase of temperature due to increase in the decomposition of the metal. Next is the semiconductors. So semiconductors are those substances which have conductivity in between the conductors and insulators. So they have their conductivity in between conductors and insulators. Next is the superconductors. So these substances have zero resistivity or infinite conductivity. That is, metals in their alloys at a very low temperature. Nowadays, a number of ceramic materials are mixed with oxides and they show superconductivity at temperatures as high as 150 Kelvin. Now we'll be studying what is the electronic conductance. So, electronic conductance through a metal is due to the movement of electrons and is termed as electronic or metallic conductance. So it will depend upon the nature and structure of metal, the number of valence electrons per atom, and the temperature. So if the temperature will decrease, then the conductivity will increase. If the conductivity is reduced due to the increase in the temperature. Pure water have very low conductivity, but when it will be mixed up with the electrolytes, then they furnish their own ions and its conductivity will increase. So the conductance of electricity by ions is called electrolytic conductance. So there is a difference between electronic conductance and electrolytic conductance. Electronic is due to electrons, while electrolyte is due to the ions. So the factors affecting is the nature of electrolyte. So strong electrolytes have higher electrical conductivity because they have large ability to ionize. However, weak electrolytes will have low electrical conductivity. Next is the size of ions and their salvation. So smaller the size of the ions of electrolyte, more will be their salvation, and hence large will be the electrical conductivity. Next is the nature of solvent and its viscosity. So in polar solvent, the electrolyte will ionize more as compared to non-polar solvent. However, lower the viscosity of the solvent, higher will be the ionic movement, and hence larger will be the electrical conductivity. Next is the heat which is provided. So on increasing the temperature, there is an increase in ionization as the movement of ions will also increase. So consecutively, the electrical conductivity of the solution will increase. So it is directly proportional to the temperature. And the concentration of electrolytic solutions. So with the decrease in concentration of electrolytic solution, that is on dilution, the ionization of weak electrolyte will increase and thus the electrical conductivity will increase. Next, we will study about the measurement of the conductivity of ionic solutions. How do we actually measure the conductivity of ionic solutions? So the unknown resistance of a conductor can be measured easily using Wheatstone bridge. However, the resistance of an ionic solution from which we calculate its conductance will be difficult to measure. So in order to measure the resistance of an electrolytic solution, the Wheatstone bridge is used. So in this method, we generally encounter two problems. The first problem is the passing of the direct current changes the composition of the solution. The second problem is a solution connection, that is the solution cannot be connected directly to the bridge. So what is the solution for the two problems? For the first problem, we can substitute the direct current with alternating current. And the second problem can be solved by using a specially made vessel called the conductivity cell, which is made up of two platinum electrodes coated with the platinum black. So this can be the structure of the conductivity cell, and the area of cross section of the electrodes is A, and they are separated by a distance L. And then we'll be able to find the resistance, and we will also understand that L by A is a cell constant which is represented as follows, and the cell constant value is L by A, which can further be written as R into K. That is the conductivity. So we can measure the cell constant by a following way, that is the resistance of the cell is measured with KCl solutions whose conductivity at different temperatures and concentrations is already known. And then the resistance of an electrolyte can be measured by using a cell that is based on the Wheatstone bridge principle. Next, we'll study how we will actually measure the resistance of unknown resistance, how we'll actually measure the unknown resistance. For this, we'll take a Wheatstone bridge setup. So in this, R2 is the resistance of the electrolyte which is to be measured, and R3 and R4 are known resistances, and R1 is variable. So R1 can be adjusted until no current will pass through the circuit, and O is the source of the AC power called the oscillator, and under the no current condition, minimum or no sound can be heard from the earphone, which is P, the detector. So when no current will pass R1 by R2 is equal to R3 by R4 according to the Wheatstone-Bridge principle. So from this we can find the R2 value to be R1 into R4 by R3. So once we will know the cell constant and the resistivity of the electrolyte in the cell, then the conductivity can be measured using the formula. And the conductivity of a solution will depend upon the charge of the ions and the size of the ions in which they will be present, and the concentration of ions and the ease with which the ions move in the solution under a potential gradient. In other words, the same electrolyte will show different conductivities at different temperatures and in different solvents. It is a very important point to note. So until now we have studied the basic terms related to the conductivity. In the next class we will be studying about the molar conductivity and the strong and weak electrolytes, Kirchhoff's law, and now we'll give a quick NCERT reading. In the previous part we have studied the Nernst equation and we have completed the electrochemical series, and the first is the Fe and the least is the lithium plus, and these are the 2 points which are to be noted. The negative E0 means the redox couple is a strong reducing agent, while positive E0 means the redox couple is a weaker reducing agent. And we have completed the equations of Nernst with electrode potential and EMF of the cell, and these are all completed, and we have also discussed how to find the equilibrium constant Kc and the electrochemical cell and the Gibbs energy of the reaction and what is the reaction at the end, and chemical equilibrium is also studied. And today we have understood some basic terms regarding the conductivity, and we knew the formulas of conductivity and resistivity and their units, and we also studied about the electrical conductance and the factors which will affect and the electrolytic conductance. And this is done. This is the conductivity cell. This is another kind of conductivity cell, and we have studied how to find the unknown resistance with the help of Wheatstone-Bridge, and we know that this is represented as the cell constant. Some questions are provided for you, and the next part will be studying and starting from the molar conductivity. Thank you so much for watching. Stay tuned for more videos. Good day everyone. Today we are going to start with the part 4 of electrochemistry. Until now we have completed until the measurement of unknown resistance. So in this part we'll be starting with the molar conductivity. So the molar conductivity is a solution. Is the conductance of the solution containing 1 mole of electrolyte kept between 2 electrodes having unit length between them and large cross-sectional area so as to contain the electrolyte. In other words, molar conductivity is the conductance of the electrolyte kept between the electrodes of a conductivity cell at a unit distance but having the area of cross-section large enough to accommodate sufficient volume of solution that contains 1 mole of electrolyte. It is represented by this symbol, and the formula is K by C, which can be written as K into 1000 by M, where M is the molarity. The units of molar conductivity are as follows. Let us solve a question. The question states that the electrical resistance of a volume of 0.05 molar NaOH solution of diameter 1 cm and length 50 cm is given. So we have to calculate the resistivity, conductivity and molar conductivity. So we know the area is pi r square. So placing the values we get the answer to be 0.785 cm square. The resistivity formula is Ra by L. By placing the values we get the answer to be 87.135 rho centimeter, ohm centimeter. And the conductivity is the opposite of resistivity. So we get the answer to be 1.148 into 10 to the power minus 2 ohm inverse centimeter inverse. The molar conductivity formula is K into 1000 by M. So by placing the values we already know the conductivity. So we get the answer to be 229.6 Simon centimeter square per mole. Now we'll be studying about the variation of conductivity and molar conductivity with respect to concentration. So the conductivity of a solution is the conductance of a unit volume of the solution kept between two platinum electrodes with unit area of cross section and are separated with a unit length. It is represented by the following formula. So it always reduces with reduce in the concentration of both the strong and weak electrolytes. This is due to the fact that the number of ions that carry the current in a unit volume of solution will always reduce with reduce in the concentration, while the molar conductivity is the conductance that of the one volume of the solution which contains 1 mole of electrolyte. It is represented by the formula. So the molar conductivity will increase with reduce in the concentration. This is because the total volume of the solution containing 1 mole of the electrolyte will increase. So when the concentration approaches 0, the molar conductivity will reach a limiting value known as limiting molar conductivity. It is represented with naught. So let us discuss for strong electrolytes. So practically, strong electrolytes will completely ionize at all concentrations. For strong electrolytes, the molar conductivity will increase with increase in the solvent. This is represented by this following equation, which is that the molar conductivity is equal to limiting conductivity minus A root C. Here A is the constant that will depend upon the viscosity and dielectric constant of the solvent, while C is the concentration of the solution. So here we can plot a graph with molar conductivity against root C. We get a straight line with a slope as minus A and intercept as the limiting molar conductivity. So the value of constant A will depend upon the type of electrolyte, that is the charges on the cation and anion produced on the ionization of the electrolyte in the solution. So this graph basically shows that the variation of the molar conductivity with root C for KCl, which is a strong electrolyte. Now we'll study for a weak electrolyte. So the electrolytes which do not completely ionize in aqueous as well as molten state are called weak electrolytes. A weak electrolyte do not get ionized completely at all the concentrations. On dilution, its alpha will increase and resulting in an increase in the number of ions. So the limiting molar conductivity value of weak electrolyte will increase steeply with dilution, especially in low concentration regions. So we can basically plot this kind of a graph against the molar conductivity with root C. This graph is for CH3COOH, which is a weak electrolyte. But the proper explanation can be provided by Kohl-Rosch's law, which we'll study in a while. First, let us see the formula of the degree of association, which is alpha is equal to molar conductivity by limiting molar conductivity. And we also have a constant whose formula is C alpha square by 1 minus alpha. Now we'll study what is Kohl-Rosch's law. He explained the limiting molar conductivity values for a number of strong electrolytes and found that the pair of electrolytes with same negative ion but differing only in the positive ions, then the value is a constant, the value of limiting molar conductivity. Similarly, with the common cation, the difference of the limiting molar conductivity values is also found to be constant. So the above observation led to formulate the Kohl-Rosch's law of independent migration of ions. So this states that the limiting molar conductivity of an electrolyte is the sum of the individual contributions of the cation and anion of the electrolyte. We can represent it as follows. That is, the limiting molar conductivity of NaCl is the combination of Na plus and Cl minus. These both individual contributions, which can be represented with a general formula as follows. Now we'll study the applications of Kohl-Rosch's law. That is, the molar conductivity of weak electrolytes at infinite dilutions can be calculated, and we can calculate the alpha at a given concentration, and we can know the alpha and also the constant K and the solubility of the sparingly soluble salts like BaSO4, AgCl, MgO2, OH2 are calculated as solubility. And the molar conductivity of weak electrolyte also depends on alpha. Higher the value of alpha, higher will be the molar conductivity. Let us solve a question. So here we have to calculate the limiting molar conductivity for acetic acid. We are provided with the limiting molar conductivities of HCl, NaCl and CH3COO, Na. So here we can find out that for CH3COOH, we can find with a combination of H plus and CH3COO negative. So by placing the individual ions and adding and subtracting the values, we get the answer to be 391 Simon centimeter square per mole. Now let us give a quick NCERT reading. In this part, we have started with the molar conductivity, and we have also completed the variation of conductivity and molar conductivity with respect to concentration, and we have studied for the weak electrolytes and strong electrolytes and the Cole-Roche law, which is the law of independent migration of ions, and we have also studied the general formula and the applications of Cole-Roche law is also done. So in the next part, we'll be starting with the electrolytic cells and electrolyte and the working of electrolytic cells. Thank you so much for watching. Stay tuned for more updates. Good day everyone. Today we'll be starting with part 5 electrochemistry of chapter 2 class 12. We'll be studying about electrolytic cells in this part. So the electrolytic cells are those cells in which the electrical energy is used to carry out the non-spontaneous chemical reactions, and the reactions taking place in an electrolytic cell is called electrolysis. It is very important to understand what is electrolysis. So electrolytic cells are those which will convert the electrical energy to carry out non-spontaneous chemical reactions, while the reactions which are happening in an electrolytic cell is called electrolysis. So the electrolysis will involve the chemical decomposition of the electrolyte by the passage of electricity through its molten or in the ionized state. In an electrolytic cell, we have an external source of voltage which is used to bring about the chemical reaction. One of the simplest electrolytic cell consists of two copper strips and which are acting as anode and cathode, which will be dipped in an aqueous solution of copper sulfate. So the diagrammatic representation is as follows. So from anode the electrons will move and they'll pass through the external source of voltage and then will again come and deposit at the cathode. And the working at cathode will be like Cu2 plus the received 2 electrons will give rise to the deposition of copper, while in the anode the copper will be broken down and 2 electrons will be released. So in the industrial purpose or processes, impure copper rod is made as an anode, and on the passing of the electricity we'll get the pure copper rod at the cathode. Here the Cu2 plus 2 electrons will give us the proper pure copper, and thus in an electrochemical cell the cations are attracted towards the negative electrode and the cathode, that is the cathode, and it will accept the electrons. Hence reduction will occur at cathode. That is in contrast to the galvanic cell in which cathode is a positive electrode. So the anode is in an electrolytic cell is positive electrode where oxidation of ions will occur, and therefore it will be in the reverse of the galvanic cell where we have the reduction at cathode and the oxidation at anode. So the applications of electrolytic cell are many metals like Na, Mg, Al are produced in large scale by electrochemical reduction of their respective cations, where no suitable chemical reducing agents are available for this purpose. Now let us study the Faraday's laws of electrolysis. So basically, the quantitative aspect of electrolysis was studied by Michael Faraday, and his laws of electrolysis are known as Faraday's laws of electrolysis. So Faraday's first law states that the amount of chemical decomposition occurring at any electrode by passing electricity is directly proportional to the quantity of electricity that is passed through the electrolyte. So here we take W to be the weight of the substance, while Q is the charge which is passing. So here W is directly proportional to Q, and we remove the proportionality sign, we get a constant Z, which is called the electrochemical equivalent, which is the amount of substance deposited when 1 ampere of current is passed for 1 second. That is the Z. So we get the final formula W is equal to Z into IT, where we can write the Q to be I into. Now the Faraday's second law. It states that when the same quantity of electricity is passed through different electrolytes connected in series, then the weight of different substances liberated at the electrodes is directly proportional to their equivalent weights. So here, equivalent weight is the atomic mass of the metal divided by the number of electrons required to reduce the cation of the metal. So we get W1 by E1 is equal to W2 by E2, which goes on to Wn by En, where W is the mass of the substance and E is the equivalent weight. Here W is the by E is a constant for all the values, so they are directly proportional. Now we'll study about the Faraday's constant. So the amount of electricity or charge required for oxidation or reduction depends on the stoichiometry of the electrode reaction. So we take this example, that is Ag plus 1 electron will give rise to Ag, which is, this is aqueous and this is solid. Here we get a Ag plus. So here we have 1 mole of the electron is required for the reduction of 1 mole of silver ions. So the charge of 1 electron is 1.6 into 10 to the power minus 19 coulombs. And therefore the charge of 1 mole, which we have to multiply with Na, whose value is 6.02 into 10 raised to power 23. So when we calculate, we get the approximate value to be 96,500 coulomb per mole. So the quantity of electricity is called the Faraday's constant, which is represented by symbol F. So by combining the Faraday's laws, we get the final expression of Z to be equal to E by F, which is equal to W by Q. Now let us solve a question. So the question is, an aqueous solution of copper sulfate CuSO4 was electrolyzed between platinum electrodes using a current of given amount for 50 minutes. We have to calculate, we have to write the cathodic reaction, the electric charge passed, and the mass of the copper deposited at the cathode. So simply the cathodic reaction will be Cu2 plus 2 electrons will give rise to Cu. This is in aqueous state and this is in the solid state. And we can find the charge, which is with the formula I into the time which is given 50 minutes. We'll convert the 50 minutes into seconds and get the final answer to be 386.1 coulomb. And we have to find the mass. Mass is equal to Zi under the time. So here equivalent weight by F. We know the formula of Z to be E by F. And after the final value would be 0.127 grams. Now the products formed during electrolysis will depend on the following factors. So the products of electrolysis will depend on the following factors. First factor is the nature of material being electrolyzed. So the products of electrolysis depend upon the standard electrode potentials of the material or the electrodes. Also, the nature of electrolyte will help us in the process of electrolysis. In case of strong electrolytes, the process becomes fast, whereas in the case of weak electrolytes and the electrodes which are being used. So if the electrode is inert like platinum, It will not participate in the chemical reaction and acts as a source and sink for the electrons. So if the electrode is reactive and then it participates in the electrode reactions. Hence, according to the what electrode we use, the electrolysis products of the same electrolyte may vary. And the nature of species present in the electrolytic cells. So here the product of electrolysis will depend upon the different oxidizing and reducing species and their standard electrode potential values. Cathodic reaction takes place with higher reduction potential while anodic reaction will take place with higher oxidation potential. And the kinetic barrier or the over voltage. So some of the thermodynamically feasible electrochemical processes are so slow kinetically that these do not seem to have or function at low voltage. Hence extra voltage or over voltage is required for them. Now let us study some examples of electrolysis. So the first example is the electrolysis of molten sodium chloride. So it produces sodium metal at the cathode and chlorine gas at the anode. So at cathode we have the reaction like Na plus 1 electron will give rise to Na which is solid. In anode 2Cl minus will give rise to Cl2 plus 2 electrons. Next we'll study the electrolysis of copper sulfate solution. So here in very inert electrodes the CuSO4 will become Cu2 plus SO4 2 negative. And at anode we have the reaction with H2O and at the cathode we have the reaction with Cu2 plus. And the copper will be deposited at the cathode and O2 will be liberated at the anode. So please write these reactions in the comment section if you understood this following equation and the process of electrolysis. Until now we have completed the electrolysis. In the next part we will be studying about the electrochemical cells in action, the batteries, mercury cells, secondary batteries, primary batteries and everything, and we will wind up the chapter. Thank you so much for watching. Stay tuned for more updates. Good day everyone. Today we are going to start with part 6 electrochemistry and we will be studying about batteries, which are the commercial cells in this part. So a battery will contain one or more than one electrochemical cells connected in a series, or it is a cell used as a source of electrical energy. It is basically a galvanic cell which converts the chemical energy of the redox reactions into electrical energy. For a battery to be of the practical use, it should be reasonably light and compact, and its voltage should not vary during its use. There are mainly two types of batteries. The first one is the primary battery, the second one is the secondary battery. So primary battery is a non-rechargeable battery. It is a device in which reactions occur only once, and after use, that is over a period of time, the battery becomes dead and cannot be reused. It produces electric current for a period of time, and with the period of time when no more chemicals remain available to take part in the reaction, the cell will not function anymore. So the most familiar examples, first one is the dry cell, also called the Leclanché cell. So it consists of a zinc container which acts as an anode, and the cathode is a carbon or the graphite rod surrounded by a mixture of powdered manganese dioxide and carbon. So the space between the electrodes is filled with moist paste of ammonium chloride with zinc chloride. This is an example of a dry cell. The reactions occurring at cathode are represented as follows. That is MnO2 plus NH4 plus 1 electron will give rise to MnOH plus NH3. And at anode, Zn will become Zn2 plus and release 2 electrons. So here in the reaction involved at cathode, the manganese is reduced from +4 oxidation state to +3 oxidation state. NH3 produced in the reactions will form a complex with Zn2 plus to give ZnNH3 raised to the power 2 plus, and the cell potential is 0.5 volts, which is produced by this cell. Uses are there used in transistors and clocks. Next we'll be going to the mercury cell, second kind of primary batteries. So it consists of a zinc mercury amalgam as an anode, and the cathode is a paste of mercury oxide and carbon. And at cathode, the reactions will occur as follows. Here the reducing agent is zinc and oxidizing agent is mercury 2 oxide. Electrolyte will consist of a mixture of KOH and ZnO. So the reaction at cathode is HgO plus OH2O plus 2 electrons will give rise to Hg plus 2 OH negative. At anode, we have the amalgam plus 2 OH and which give rise to ZnO plus H2O plus 2 electrons. So the overall reaction will be as follows by adding these two reactions. And here the cell potential is approximately 1.35 volt. And it remains constant as in the overall cell reaction no ions are involved in a solution whose concentration can change during the lifespan of the cell. It is very long lasting. And the uses of mercury cell are they useful for low current appliances like hearing aids and watches. Now we'll be moving to the secondary batteries which are rechargeable. So a secondary cell after one use can be recharged by passing current through it in the opposite way. A good secondary cell can undergo a large number of charging cycles and the reverse cycles as well. So the well-known example is a lead storage battery. So a lead storage battery consists of lead anode and a grid of lead packed with lead dioxide as cathode. A 38% solution of sulfuric acid acts as an electrolyte. When the battery is in use, then the cell reactions are at cathode. We have PbO2 plus SO4 2 negative plus 4H plus 2 electrons will give rise to PbSO4 plus 2H2. At anode, we have Pb plus SO4 2 negative will give rise to PbSO4 plus 2 electrons. So by adding these two reactions, we get the overall reaction to be Pb plus PbO2 plus H2O SO4 to give rise to PbSO4 plus 2H2O. So the potential of the battery is 2 times the number of cells present in it. So if we have a battery with 3 cells, then the potential will be 6 volt. And if we have a battery of 8 cells, then the potential will be 16 volt. During charging, the current greater than 12 volt is passed from the external source. Due to this, the reactions are forced to be reversed and PbSO4 on anode and cathode is converted into Pb and PbSO4 as PbO2 respectively. So it is used in automobiles and power inverters. Now we'll be moving to the second category of the secondary batteries, that is nickel cadmium battery. So it consists of a cadmium anode and a metal grid contained of nickel O2 as cathode. KOH solution is the electrolyte. So the reactions can be written as follows at the cathode and anode, and by adding these two reactions we get the overall reaction to be Cd plus 2 NiOOH plus H2O will give rise to NiOH twice CdOH twice. So when we are using the battery, then this reaction will follow and this voltage of the cell is 1.4 volts and it has longer life than the lead storage, but it is more expensive to manufacture. Next, we'll be moving to the fuel cell. So, it is a galvanic cell in which chemical reaction or the chemical energy from the combustion of fuels like hydrogen, methane, methanol is converted into electrical energy. In this galvanic cells, reactants are continuously supplied to the electrodes which react to produce electricity, and products thus formed are continuously removed from the electrolyte department. One of the most successful fuel cell uses in the reactions of hydrogen with oxygen to form water. It is used in Apollo space programs. So the water vapors produced during the reaction were condensed and added to the drinking water supply for the astronauts. So in this cell, hydrogen and oxygen are supplied through porous carbon electrodes into concentrated aqueous sodium hydroxide solution. Finely divided platinum or palladium is incorporated into these electrodes which act as a catalyst. So the reactions which are happening are O2 plus 2H2O plus 4 electrons will give rise to 4OH negative, and at anode we have 2H2O plus 4OH negative will give rise to 4H2O plus 4 electrons. So overall reaction is 2H2O plus O2 will give rise to 2H2O. This water is produced after the overall reaction. So the advantages of fuel cells, it is highly efficient, that is 70% in comparison to thermal power plants which only give 40% of efficiency. It will not cause any pollution as no harmful products are formed. It is only water which is formed after the overall reaction. And this cell runs as long as we provide hydrogen and oxygen. And this cell, being lightweight, has been used as automobiles on an experimental basis. So in this part we have completed the primary and the secondary batteries in the fuel cell, and we have completed all the batteries part, which are the commercial cells of chapter 2 electrochemistry. Thank you so much for watching. Stay tuned for more updates.